Okay, does it work? Yes. But okay, so I want to discuss this semi-continuity result. So first I will state it again, because the statement I gave last time was just a sketch of a statement. Okay, so I will use the words of Junyi Xie, okay, which are not mine, but are the good ones, okay. So here, what is a family? It's very loud. Can I change this? Yeah. So it's what is a family? So a family of d-dimensional dominant rational self-maps or rational transformations is what? So it's the following data. So it's given by a projective how to say that? A flat projective morphism phi from X to S, where I mean, I don't want to put all the details, okay? So S will be some scheme, some integral scheme, okay? And with F from X to X, a rational transformation okay. Such that what? So you want it to be above S. And so now I want to justify all the terms over there. So first, the relative dimension of X over S is D, so this is for D-dimensional dominant self-maps. So second thing you want, second thing that Junyi is adding to the definition is for every S in S, the fiber X index S of pi is geometrically reduced and irreducible. So this is part of his definition. Third property, for every S in S, XS is not contained in the indeterminacy locus of your map F. So for every S in S, F induces a rational map F index S on XS, and you want it to be dominant. Oh, yes, you're right, in the exceptional locus of... okay. I mean, it's you can put indeterminacy here because then when you reduce, when you induce f on xs, if it were contained in the exceptional locus, then it could not be dominant. Yeah, there are some kind of redundancy. So this is why I put in here. Also, you can forget about this dominant I wrote at the beginning. But the idea is to list all the good properties. And in fact, after that, you can take more general families and make some base change to achieve what you want. But I really want to state the theorem as Junyi stated it because that's what I want to do. Okay, so the degree of generality that, so this is a family of d-dimensional dominant rational safe maps, let's say parametrized by S or over S. And now what Junyi does is he does it for any integral Noetherian scheme. Okay. And then you take a family like that. So let F, I will denote by F the family, be a family of d-dimensional dominant rational self maps over S. Then we have semi-continuity of the dynamical degree. Okay, so for each codimension P, the dynamical degree lambda P, so which takes a point in S and computes as a dynamical degree of F restricted to the fiber, is lower semi-continuous in the Zariski topology. Okay, of S. Okay, so I stated it like that. So that's the way Junyi states it. You want to include geometric situations that I discussed yesterday on examples, as well as more arithmetic situations when you have families which are defined over Z and you reduce mod P. Okay, so that's the statement. Yesterday I didn't state it properly, now I did it. What I want to do is discuss the behaviors that are hidden behind this statement. Yes. 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 You are not using a Keller geometry anymore. Yes. So you are using so dynamical degree. Let me remind. So you compute this limit. Okay. Okay. That's it. Let me write it like this. It's a polarization on XS to intersect it P times, and now you intersect with D minus P copies of it, 1 over n. Okay, and this intersection, you have to define it. You know, you look at the graph of Fn, and you pull back by the two projections these two things on the graph, and you intersect on the graph. Okay, so I won't have time to prove this result, and in fact, I never planned to prove it in like this, but I want to explain what's going on and some of the ideas when the relative dimension is d. Okay. So first, why did I insist here what I mean by the Zariski topology and so on? I'm looking at S as a scheme, okay? And this is a good point, the good point of view. So let me explain why. Okay, so assume, let's say S is a curve, okay, and everything is defined over Q bar. Okay. Then I can look at S of Q bar, the Q bar point of S. Okay, and let me discuss this statement if the statement were only semi-continuity with respect to the Zariski topology on the Q bar point. Okay. As a set, this is a countable set. So I can label the points by n, by the integers. Okay, I have a one-to-one map from the set of points to n. So fix such a one-to-one map. Just a bijection from this countable set to the integers, positive integers. So what does semi-continuity mean? So semi-continuity, I have to check the following. So for every beta in R, so let's call this function phi. I want to know whether this function is semi-continuous. What do I have to check? So it's a function with value into n, in fact, into R. Okay, and I have to look at the sub-level sets. So the set of points x in S of Q bar here, such that phi of x is bounded from above by beta. Okay, and the question I am asking is this set closed? In the Zariski topology for every beta. Okay, so that's the question that you have to address if you want to prove lower semi-continuity. So you have to show that these sets are closed. And yes, there are, because if you fix any beta in R, there are finitely many integers below beta. And so there are finitely many points where this property is satisfied. So, okay. So this set S beta is finite for every beta. And so this map from this set to R is lower semi-continuous for the Zariski topology induced on this set. Because finite set is Zariski closed. Okay. So this map is semi-continuous. It's not a map which is defined on the scheme, because if you have a semi-continuous map as a map defined on the scheme, you can take the generic point. So now let eta in S be the generic point. And suppose H from S to R is semi-continuous in the Zariski topology. but for S as a scheme. Then I can evaluate H at the generic point. I get some number. And lower semicontinuity tells you that every point which is in the closure of eta must correspond to a value which is at most h of eta. Okay, so this is a consequence of lower semi-continuity. Okay, so with the point of view which is here, Zariski topology for my scheme, in fact, every lower semi-continuous function is bounded from above. Okay. So this function phi, the restriction of, I mean, for the function phi, you cannot extend phi to a function on the scheme which is lower semi-continuous, because this phi over there is not bounded from above. Okay? So the statement stated like that includes corollaries which are better than if you just think about points over the algebraic closure of your field of definition and lower semi-continuity for the Zariski topology on this set. Okay, is that clear? Okay, so what is the meaning now of lower semi-continuity? Function phi from S to R is lower semi-continuous. If and only if it satisfies two properties, A and B. So what is A? For every x in S, for every y in the closure of X, h of y is at most h of x. So that's the first property, which I used here to say that. And the second one is for every x in S, for every number beta which is strictly less than h of x, the set of y in the closure of X such that h of y is larger than beta contains a dense open subset of X bar. Yeah. Okay, so I will not prove the lemma. It's easy just playing with Zariski topology and the basic definition of being lower semi-continuous. Okay, but let me mention a corollary. If, let's say, I will state it without being super precise, but let's say if f from x to x is defined over Z, let's say x is the affine space and f is a birational transformation of x, which is defined with formulas with integer coefficients. Then you can look at f modulo p for some prime p, compute lambda, oh, p is not good, not lambda I of f, and look at the limit when p goes to infinity, then this has to be lambda I of f on x. This is exactly that. So, in fact, it's a limit from below. Okay, so that's it. Okay. if you take a generic sequence of points converging to the generic point, then along this sequence, the limit of the lambda I is equal to lambda I at the generic point. Okay? So this is part of, this type of things is part of the statement. So now I want to explain semi-continuity of degrees instead of dynamical degrees. Okay, so here is the proposition that you can prove. And I will prove it in a specific case. So let me precise the notation, be the d-dimensional family of dominant rational self-maps, like that. Okay, and you fix an ample line bundle on X. Okay, so I will, if you take S in S, you can restrict and you get, let's say, L index S is the restriction of L on X index S, which is the fiber above S. Okay? And then you compute the following things. You can, to S, you can associate just the intersection product. So F to some power or Ls intersected with F to some other power, on S, Ls, etc., up to F m to another power md star Ls. Okay, and you get a map from S to the set of integers. Okay, and this map is lower semi-continuous. Okay, so in particular, if you compute something like S goes to Fn star of Ls to some power k, and then you, let's say I, and you intersect with Ls d minus I, this is lower semi-continuous. Okay, this is just exactly this statement, but for the I first terms, you take m1, mi, etc. equal to n, and for the last one, you take the mi to be 0. Okay, so let me sketch the simplest case to explain the phenomenon. Okay, say S is just the line with parameter t. Oh, sorry, S in S. Okay, and F is a family of dominant rational self-maps of P to the D. Okay? So then you can write it like that. F index S is what? It's x0 up to xd goes to p0 up to p d, okay, comma t here, where the pj t of the xi is a homogeneous polynomial of some degree, which I will denote by delta, with coefficients in the function fields, let's say, in one variable. So what is the field? It's I didn't specify the field, so k of t. Okay, I can write it like that. Okay. So what is just a rational transformation of PD, so I can write it using homogeneous coordinates and homogeneous formulas. And I don't want any common factor for these polynomials, say, of positive degree. Okay, so the point is that now, what is the semi-continuity? So the generic degree is delta. So here I'm looking at lambda d. But when we specialize, what the degree might drop. This is exactly the phenomenon that is appearing in these things. Okay. And when does it drop? It drops when there is a common factor which appears in these formulas. And so what is the condition that ensures that the degree does not drop by something positive? It's described by some resultant in these polynomials, which becomes a function in the variable t. Okay, and when this function is 0, there is a degree drop. But the locus where the function is 0 is a Zariski closed set because it's given by an algebraic function. Okay, so this is the type of phenomenon you see. Okay, so I didn't prove anything. I just explain what happens in this very specific case when you compute the topological degrees. Okay. Okay, so what is the phenomenon now for this proposition in full generality? Okay, so what you use is when you compute this type of intersection products, if everything is flat, the number you get is just constant. Okay, and here I'm saying that it's lower semi-continuous. Why is it so? It's because when you do this composition, you do it on the graph of f, and the family of graphs is not a flat family. There are discontinuities. Okay, so this I want to explain. In fact, I already explained it yesterday, and I want to come back to this type of examples. So, back to multiplication by -2 along a family of elliptic curve. Okay, so you have a question, Claudia? No. No. It depends. I mean, it depends what you are asking for. If you fix a flat family, okay, a flat projective morphism, and you compute some very specific intersection product along this family, then it might vary. I mean, it might be constant without the family being flat. But if you ask it for all Hilbert polynomials of everything, this is basically the definition of being flat. Okay? So in some sense, the answer is yes, but if you are interested in just one specific intersection product, so the answer is no. Okay. Okay, back to multiplication by -2. So now I will so do the example I was doing yesterday like that, and you look at the map which is given by this construction. But I will draw it a little bit differently, slightly more general. So you have a surface X that fibers above a base S, and the general fiber, so I like complex geometry, so I drew a general fiber which is a genus 1 curve, okay? But some fibers, like this one or that one, become singular with the simplest singularity, nodal singularity, okay? And now assume you have a section like that. So I can look at the intersection point with the fibers. Okay. And I can declare that this intersection point is a neutral element of my general fiber. So then I get an elliptic curve, and I can define a rational transformation f, which is multiplication by any integer d on this thing, and I choose, let's say, by -2. Okay, I can do that. So this is slightly more general, but this is the same phenomenon that here. Okay, what happens when you do these computations of degrees? So here you have to compute the topological degrees. If you go back to the definition here, you have to first to compute the graphs of your maps and the graph of the iterates, okay? And then you pull back your classes on your graph and you intersect. So what you have to do is understand what happens to the graph of this map in each fiber and how it degenerates when you arrive at the specific fiber. Okay, so the graph at a generic, a general point, okay, is something in the product of an elliptic curve by itself, and it's a graph of multiplication by -2. You see, it's a thing like that. Okay, it's a smooth elliptic curve in a product of an elliptic curve by itself. Okay, and then you take a point, you pull back, and you intersect with a vertical, and you get the number you want. It's the topological degree. Okay, and what is the limit of these graphs when you arrive here? Okay, as I explained yesterday, here there is an indeterminacy point. Okay, so the map is not well defined here. You have to blow up this point, you get a curve, and this curve comes with multiplicity 2 and is mapped to this one. Okay, is it clear? And then at the limit, in the limit of the graphs, you get two irreducible components. The first component is you restrict your transformation to the curve minus the indeterminacy point. You take the graph, and then you take the closure. That's one piece of the limit. But there is another piece, which are points, which are, I mean, pairs of points in the exceptional divisor. Okay? So where am I computing these graphs? Okay? It's not something you see in this curve times this curve, but I have to desingularize this, and I compute this limit in this desingularization. Okay? So what is happening is that this intersection product, they are constant along flat projective morphisms if you look in the fibers. In this direction, if you look at the graph, which is now something in higher dimension, you project on S like that, just flat. But if you project using the transformation F, it's not flat anymore, and you have to desingularize and do a base change, and so you change the variety, and the limit of these graphs is reducible with two pieces. The first piece, I say it again, it's just a restriction to this curve when you remove the indeterminacy point, and this contributes to what you compute when you compute the degree of the restriction. Okay? But there is something coming from the indeterminacy point. The indeterminacy point, you see it because of this family. Okay? So there are two positive contributions, the one you see on this curve at the general point, and the one coming from the indeterminacy point that you don't see when you specialize. Okay? So this is the phenomenon that is that you see in this proposition. Okay, so when you prove this proposition, this is the type of thing that appears and explains why the degrees are not constant but lower semi-continuous. And when you want to understand the dynamical degrees, you have to understand this type of pictures and the type of degeneration that the graph have, but not just for one map, but for all the iterates. Okay, so you do a first iterate, and then there is some kind of simplification which comes from the singularities of the graph, and then you iterate again, and there is another simplification, and so on. So the theorem of Junyi Xie is taking care of all these type of simplifications or degenerations for all iterates, at least at the limit. Okay, so in some sense, it's quite impressive, okay, to be able to do that. Okay, let me do another example. So first, I do just one transformation, or a group of transformation. So here my space is P1 times P1 times P1. Okay, and I take a surface in this three-dimensional space, so something of codimension 1. And let me do a picture like that, which is smooth and has degree 2 with respect to each of the variables, the three variables. So this means that when you project this surface on P1 times P1 by forgetting the third variable, you get a ramified 2-to-1 cover. Okay, and the same, I'm asking the same for the three variables. So if you project from forgetting the y variable, you also get a 2-to-1 cover, and if you forget the x variable, you also get a 2-to-1 cover. So it's a surface of degree 2, 2, 2. Okay. If you have such a surface, you have three natural involutions, which are the deck transformations of these 2-to-1 covers. So it comes with three involutions, S1, S2, S3. Okay. And these three involutions are automorphisms of X. It's not completely obvious, okay? Because what might happen is that there is a fiber which is contained in the surface, a P1, a vertical P1, and then how do you define this deck transformation along this fiber? Okay, it's not clear. But in fact, this surface is a K3 surface. It's a minimal surface, and so there are all birational transformations are automorphisms. So you know that there are automorphisms. Okay, and then you can look at F, which is just the composition of the three. in the group generated by the 3 involutions. So this is an example of an automorphism of a K3 surface such that, so it's an automorphism, so lambda 0 and lambda 2 are equal to 1, but lambda 1 is larger than 1. Okay? So you can do the computation explicitly for the action on Néron-Sévry group or cohomology. If I remember correctly, the lambda 1 is 4 plus square root of 5 divided by 2. Completely explicit. Okay. So that's just one example. For the moment, there is no family. So now I add a variable. Okay, so I have x, y, z, my first coordinates, and I'm adding one more variable which I call s, and this p1 will be my parameter, capital S. And again, I assume that it is smooth of degree 2, 2, 2, 2. But the transformation I consider is this S1 composed with S2 composed with S3. It does not act on the last variable. So I have a family of automorphisms on a family of K3 surfaces. And globally, this capital X is, in fact, a Calabi-Yau threefold fibered into K3 surfaces. Okay. And globally, F, if I look at its action on this, it's a global birational transformation of this three-dimensional thing, which on each fiber is an automorphism. What is the behavior is the following. So you imagine that you have your surface X sub S for some parameter S, and you let S vary. For the general, so assume that for some S, there is no vertical line or horizontal line or line parallel to the P1 with the X variable, which is contained in XS. Okay, then this will be satisfied generically or generally. But so for some parameter, specific parameter S, you will see that, for instance, a line is contained, a vertical line like this is contained in X S0 for some parameter S0. And you can count the number of phenomena like that. Okay. Then along this line, this birational transformation makes a flip. You blow up the line, you blow up the P1, you get a P1 bundle above this P1, and then you contract this P1 in the other direction. Okay, so you have a birational transformation which flips a line. Yes, but this, yeah, I forgot about this. Okay. You also have singular fibers. Okay, and what happens, even if you have a family of maps which individually, each of them in restriction to XS is an automorphism, as a family is just a birational map, and what you see is this lower semi-continuity phenomenon. Okay. In fact, you can even construct example for which the group becomes trivial on a specific fiber. Okay. So this has been studied in details by, in this specific example, Peschke plus Reutemann. They computed the dynamical degrees. And the general phenomenon for K3 surfaces, there is a nice paper by Ogiso on that. Okay, so now I want to explain some of the ideas, or not really the ideas, but the intermediate statement you might use to prove the semi-continuity theorem in the simplest non-trivial case, which is the case of transformations of surfaces. So this is the case when the relative dimension is 2. So we have a family of rational transformations. X has dimension 2. Okay. And so we have to compute a priori lambda 0, lambda 1, lambda 2. So this is 1. This is a topological degree. Okay, so this is the number of preimages of a generic point. So this one is easy to control. So what I will study is lambda 1. So I have to fix, so on my family, I fix an ample line bundle, and I denote again by L sub S, a restriction of L onto XS. Okay. Okay, so I have these two properties. I think I already erased them. I want to show what? I want to show if X is in S for every Y in the closure of X, I want to show that lambda 1, or maybe my notations are not very good, but for every S in S, for every T in the closure, I want to show that lambda 1 at Ft, when I specialize, it is at most lambda 1 of F at the point S. Okay, so that's the first thing I want to show. The second thing I want to show is for every S in S, for every beta which is less than lambda 1 of Fs, there exists U in the closure of S such that as soon as I take a parameter T in U, the value I compute is larger than beta. Okay, so these are the two properties I want to obtain. So first property, okay, so I will, instead of doing it for all S in S, I will do it at the generic point. Okay, I take S to be the generic point. And I want to prove these two properties at the generic point. Otherwise, I just replace S by the closure of my point, and I'm reduced to that case. Okay. Okay, so denote, for simplicity, denote by degree of Fs in codimension 1 to be this intersection product that I am interested in. Okay? Just I'm not specifying the line bundle here, even if it is important in the definition. And I will also forget about the fact that it is degree in codimension 1 to simplify the notation. Okay. So with this notation, lambda 1 of F at the generic point is what? It's the limit of degree of F iterating n time at the generic point, and you take the nth root. In fact, it's even the infimum of that. Okay, so you can pick n large such that this is less than that and larger than sorry. Minus epsilon. Okay. So this, in fact, I won't use it. I will use it, but so now I want to know what happens when I replace eta by some parameter t in S. Okay. And I just use the proposition, the semi-continuity of these degrees, yeah, which is just the fact that under flat morphisms, the intersection products remain constant. So for degree of Fn at a point t power 1 over n, so the degree is less than the degree at the generic point. Okay, this I know from this proposition. And now I take nth root. Okay. And now I apply the definition of the dynamical degree for f sub t, and this is okay. This I know. Okay, from the proposition here. Okay, and then you take limits, okay, and by construction, the limit here it will be lambda 1 at the generic point. And here, at the limit, you will get something which is bounded from below by lambda 1 at f sub t. Okay, so the first thing here, the first property, is really nothing else than the existence of the dynamical degree, so the existence of this limit, plus this semi-continuity, okay, which is easy. What is hard is the other direction. And what is the theorem that you can use in the other direction? So it's for property B. It's the following theorem. Let F be a rational dominant self-map of a surface. Then you get a lower bound for lambda 1. It's always bounded from below, sorry, by the degree of the second iterate divided by the degree of f up to some factor 1 over 4. So, I mean, this statement, you can prove it by using the techniques that Charles Favre described last week. So this Hsu's criterion for big and F divisors, or Hsu inequality that he described. Okay, and the proof is really, you can prove it using that. Okay. It's not harder than what Charles did last week. Okay, it's even simpler. Okay. you can also prove that, and this was the first proof of Junyi Xie, when f is a birational transformation of a surface, by looking at the action of f on the infinite dimensional hyperbolic space that Stefan is describing. Okay, so it's also a consequence of hyperbolic geometry when f is birational, except that the constant 4 that you have here is not as nice when you use this type of hyperbolic geometry. You get a constant which is like 10 to the 18 or something like that. Okay, but it's not important for the argument. May I sketch the argument? Yes, I will take 3 minutes to sketch the argument. How do you use that? Okay, to prove the second property B. Okay, so lambda 1 of f is limit with this notation degree of fn to the 1 over n. Okay, so lambda 1 of f. So what I'm saying is that, let me write what I want. So there exists n0. So you fix beta less than lambda 1 of f. Okay. So you can approximate a lambda 1 from below and above beta by this type of things. There exists n0 larger than 1, such that lambda 1 of f is larger than degree of fn0, 2n0, or degree of n0 divided by 4, 1 over n0, and this is larger than beta. Okay. This is just because, this I don't care much. Okay. This is just because this thing here, when there is a factor 2, and I divide by, I take the nth root. So what I get roughly is lambda 1 square. I divide by something which is roughly lambda 1. So the ratio is roughly lambda 1. And the 4 to the 1 over n0 is roughly 1. Okay, so this is roughly lambda 1 of f. Okay. And so since beta is less than lambda 1, I can do that. Okay, so here I apply it at the generic point. Okay. But now I fix n0, and I look at these numbers, this degree and that one. So the degree, the function t goes to degree of f, let's do the lower term, n0 index t. But again, by the proposition, which I erased, is lower semi-continuous. Okay, and the possible values are finite. It's a degree. Okay, so you get positive integers which are bounded from above by the integer you get at the generic point. Okay, and so by the lower semi-continuity of this function and property B for this function, there is an open set on which, a dense open set on which this function is arbitrarily close to that one. But because these are integers, as soon as it is a distance less than 1/2 of this one, it's equal. Okay, so it says, by lower semi-continuity, there exists an open set, let's say U1, such that this degree is equal to what you get at the generic point. Okay. You apply the same argument and you get an open set, a dense open set U2, for which the degree of the iterate number 2n0 is equal to the generic degree. Then on the intersection, this ratio is the same after specialization. But from this proposition, this means that lambda 1 at f index t is larger than this ratio, which is equal to this one, so it's larger than beta. Okay. Very basic now. Okay. That's the end of the proof. Okay, I constructed an open set, which is dense, on which lambda 1 of f sub t is larger than beta, which is exactly property B. Is it clear? I think I have to stop. That's why at the end I did it quickly. But okay, that's it. And so that's the end of the proof in this specific case, without proving that, which you can prove with the techniques from last week. Yes. Are there some automorphisms? No, never. So for an automorphism, you cannot have equality because for birational transformations, yes, if you take no, because of this factor 4. If you remove the factor 4, there are examples. With the factor 4, I don't think so. So we don't know we don't know yet what is the best factor here. Maybe 4 is the best one, but I think there is no known example that realizes this equality for birational transformations. For regular automorphisms, you cannot have equality because this is a rational number, and lambda 1 of f is never a rational number for automorphisms, or it is 1. Yep. For what? Oh, for the moment, it's not written in the Keller case. Okay, so I think it works. We have to write the proof. Okay, it should work. No, we are using this U inequality, so we are using line bundles which are big enough. So if you have such line bundles on your Keller manifold, you are projective or very close to be projective, okay? You're like Moisheson or something like that. So for the moment, the proof does not work, but it should work.